Hello, I'm Discordian, and today we're going to be talking about bits, starting at what they are, how we represent them as integers, and manipulating them via bit shifting and bit masking. We'll be using big endian for our numbers, which basically just means they'll be read from left to right. But if you want to know the difference between little and big endian, feel free to ask below. If you'd like to skip to a specific section, I have different sections timestamped in the description. So, you probably hear about bits all the time. You had 8 and 16-bit gaming consoles, you have 24-bit color, you have 32-bit and 64-bit computers, you have 128 and 256-bit encryption keys. But what do these really mean? Well, a bit is what people are talking about when they talk about binary in regards to computers. A bit can either be on or off, so understanding binary numbers is fundamental to understanding bits. Also, there are 8 bits in a byte, so if you have 10 bytes, you have 80 bits. Or, if you have 256 bits, you have 32 bytes. Let's do a simple example. We have 8 bits. They're all zeros. This is also 1 byte. This sequence represents the number 0. You can see to the right of the number, we have a hexadecimal representation, 00. These two hex digits represent a single byte, and it will update along with the other numbers we'll use here. Hexadecimal, also known as base 16, is used as a convenient way to represent data instead of raw bits. However, without an understanding of what the bits are doing, the hex might mean little to you. We can add 1 to it. This is 0 plus 1. And this is our new sequence. And it's still 8 bits, but now it represents the number 1. And we can add 1 more. And so now we did 1 plus 1. And this sequence represents the number 2. Using these 8 bits, we can represent 256 different values. Let's animate that. So you can see once we populate all of the bits with 1s, we end up with the highest number, 255. The 256 value, of course, being 0. This is true for an unsigned 8-bit integer at least, but what if we wanted to represent negative numbers? Well, let's start over. So these 8 bits still represent the number 0. And we can still count up to the number 127, just like normal. However, if we treat this as an unsigned 8-bit integer, and we just add 1 more in binary, we actually end up with negative 128. Despite our hex representation being what would be, I guess, regular 128, and our binary as well, we can continue to add 1 to this. And you can see then it starts adding to it normally. So it's actually counting down from 128. So negative 128 to 127 to negative 126. This is what's referred to as an integer overflow, because we've overflowed past our 127 limit. So we can actually do this all the way to negative 1. So what you're seeing here is the first bit is effectively a flag, indicating if it's negative or not. It jumps down because of something called 2's complement, which is a way of representing numbers effectively. It's a totally different topic, which I will link in the description below. But 2's complement allows us to also represent negative 128 to 127 as an option within our 8 bits very effectively. And this is typically like what a signed 8-bit integer would be. But we can expand our bits from 8-bit to 16-bit. And we end up with exponentially more options. From 256 to 65,536 possibilities. You can calculate this number with 2 to the power of 16, or however many bits you want. Understanding bits helps us understand things like why 32-bit computers had a 4 gig RAM limit. The 32 bits refers to the register size, so, and this is oversimplifying it, this effectively means the processor can only instantly comprehend a number of 32 bits in size. So if we take the total possibilities for a 32-bit number, which is 4,294,967,296, then divide it by 1024 to the power of 3 to get the size in gigabytes, we get a clean 4 gigabytes. If you've made it this far, you're probably wondering, what does knowing anything about bits do for me? And what can I do with them? Well, in my opinion, the answer is exciting. Using bit manipulation techniques, people accomplish all sorts of things. But we'll use a simple example of storing 2 numbers into a single byte and then retrieve them. If you wanted to try anything you've seen in this video, I'll be showing the operators I'm using on screen, so you can try it out in Python or your favorite programming language. I'll also link calculators below so you can experiment with bits that way if you'd prefer. So sometimes you want to optimize how you store numbers. For example, if you wanted to store several chessboard layouts, you know your coordinates are only going to be up to 7 on the X and 7 on the Y. So if you wanted to have a board with a black rook on position 5, 6, you'd store something like R56 or 3 bytes. Seems fine for one piece, but when you have boards of 32 pieces and you have a lot of boards, it begins to add up quite quickly, possibly wasting 1/3 of your storage space. However, we know that 2 to the power of 3 is 8, and we only need 8 numbers. Then we know that we could store both those numbers into 1 byte, as we really only need 6 bits for both numbers. But how do we actually do that? The answer is actually quite simple. We'll need to learn about bit shifting and bit masking to properly store and recover our value of 5 for the X and 6 for Y. We start with bit shifting 5 to the left 4 times. We'll set these numbers here. And what this does is it shifts it over by 4 bits. As you can see, now our number appears to no longer be 5, but you can still see the 5 in our hex and binary representations. We got our 5 here, and now our 5's over here. Even if it appears to be 80. But that's it as a base 10 integer. All we've done is move it over to the left 4 bits, filling in the bits on the right side with zeros. Next, we simply add our y coordinate in by adding 6 to our current number. Alright, so we'll fill in 80 as our number 1, and 6 as our second number, and then what we are going to do is just add that in. So now we can see our numbers combined in there. On the left 4 bits we have 0, 1, 0, 1, which represents our x coordinate, 5. On the right 4 bits we have 0, 1, 1, 0, which represents our y coordinate, 6. The hex also shows us this as it's 5, 6. So of course we have our x, which is 5, and then our y, which is 6. As an unsigned 8-bit integer representation, it's 86. And that's not very useful to us. So how do we extract our coordinates if we need them later? First, we can extract the x coordinate using what we already know, and that's by simply bit shifting to the right 4 times. We fill in our 86 here, number 1. Of course, number 2 is going to be 4. We're going to bit shift to the right. There's our 5. So how do we get the y coordinate? Let's go back to our combined number, which of course is 86. So what we did to get x was move everything over, effectively replacing the right 4 bits with the left 4 bits. Now we simply want to retrieve the right 4 bits. We can do this with bit masking. We're going to use a mask that effectively says we just want the right 4 bits returned, with the rest being zeros. We'll use bit AND to accomplish this. A mask allows us to specify what bits we want to return by setting the desired bits to 1 in the mask. So I'll show our mask in number 2 here, so you can see our right 4 bits are all 1. And we run that. We have now quickly retrieved our y coordinate of 6. What exactly have we accomplished here? Well, remembering that in computers we work with bytes, so if we wanted to store 2 numbers, we would typically need 2 bytes at least, or 16 bits. Looking at our requirements, we only need 6 bits, so that seemed excessive. Using this simple technique though, we've reduced our usage down to 1 byte via bit manipulation, and we've only wasted 2 bits. Well, that's it for this video. I really hope you learned something, and if not, I hope my video had whatever you were looking for. If you'd like me to go further into bits, like the XOR operator, or maybe other examples, please ask below in the comments. If you liked this video and would like to see more videos like it, please tell YouTube you like it by hitting the thumbs up icon and subscribing to my channel. It'd really help me out. Until the next video, see ya!